Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss the brief revision of complex number and its graphical representations. Let's begin. Let you take a quadratic equation as x square plus 1 is equal to 0. This type of quadratic equation, when we solve, we have x square is equal to minus 1 or x is equal to under root of minus 1. Till now, we studied the number system up to real numbers. Real numbers as the combination of both rational and irrational numbers. The number systems up to as natural numbers, integers, rational numbers, irrational numbers, all these numbers are under the category of real numbers. But under root of minus 1 is not in that of a real number system. So, there is a necessity to introduce a new type of number system. Therefore, a new type of number system is introduced named as complex number system. Complex number system. So, a complex number, we can express a complex number as expression of complex number as z is equal to x plus iy. Here z is the complex number x and y are the real numbers. X and y are the real numbers, and that part is known as the real part, and this part is known as the imaginary part. As I is equal to minus 1, which is known as the imaginary number. And we pronounced the term I as iota. We pronounced it as iota. And x and y are real numbers. That will be the representation of a complex number. Z is equal to x plus iy. Again, that can be further represented as, if I write real part of z, real part of z, REZ means real part of that complex number z. So, we have real part of z is x. If I write the imaginary part of z, imaginary part of z, I am z, here the imaginary part of z that is y. That is the real part of z, r is z. That can be studied as the imaginary part of z. If in that particular term, if x is equal to 0, if x is equal to 0, then that complex number z is said to be pure imaginary. Then z is said to be pure imaginary. Similarly, if y is equal to 0, then that complex number is said to be pure real. Then z is equal to pure real. Again, there will be another notation to write that complex number z is equal to x plus iy. Another notation, z is equal to x plus iy can be written as z is equal to x comma y. If we prefer some examples, if a complex number 4 plus 5i, then find out the real part and imaginary part of that of given complex number. Since it contains the imaginary number, so it is the combination of real number and imaginary numbers, that is why that is a complex number. Here 4 is the real part, 5 is the imaginary part. An important note here, we introduce iota under root of -1. Therefore, the square of I is equal to -1. Again, I q is equal to I square into I square is equal to -1 into I, that is minus I. Again, I fourth is equal to iq into iq minus I into I, which results minus I square means minus minus plus, so that result will be 1. As we proceed in this manner, look that sequence here 2, 4 and so on. Therefore, I to the power 2n is equal to I square to the power n, I square is equal to -1 to the power n, that results is equal to 1. if that n is even and that results -1 when n is odd. But same thing, I to the power 2n plus 1 is equal to I to the power 2n into I to the power 1, I to the power 2n into I to the power 1. So, that results will be 1 if n is even, and that results will be that is I, that is minus I if n is odd. We have to remember that sequence. First, the value of square of i's. Next, algebra in complex numbers. Complex algebra. Basically, algebra means it is the combination of 4 operations as addition, subtraction, multiplication and division. These algebraic operations are hold good in case of complex numbers or not. Let we see. Let us consider two complex numbers, as z1 is a complex number having x plus iy, or we can say that is x1 I y1, and another complex number z2 as x2 plus I y2. First operation, addition. Z1 plus z2, z1 plus z2. In place of z1, it is x1 plus iy1 plus z2 x2 plus iy2. Now, we have to combine the real parts and imaginary parts. So, the real parts x1, here the real part x2. So, x1 plus x2 plus imaginary parts I as common y1 plus I2. So, that can be written as x1 plus x2 comma y1 plus y2. That is the another way to represent a complex number. So, addition of two complex number results a complex number. Next, another algebraic operation, that is subtraction. z1 minus z2, x1 plus I y1 minus x2 plus I y2. Subtracting the real numbers, subtracting the real parts, x1 minus x2 plus I y1 minus y2, that is written as x1 minus x2 comma y1 minus y2. So, the subtraction of two complex number results a complex number. Next, multiplication. Z1 into Z2, x plus I1 into x minus x1 plus I y1 into x2 plus I y2. First x1 is multiplied in that term. So, x1 is multiplied the term x2 plus I y2 plus I y1 is multiplied to that term x2 plus I y2, x1 x2 plus I x1 y2 plus here I x2 y1 plus I square y1 y2, x1 x2 in that term y taking as common we have x1 y2 plus x2 y1 I square is equal to minus 1 y1 y2 as I square is equal to minus 1. So, x1 x2 minus y1 y2 plus I x1 y2 plus x2 y1, that bracket term, that is the real part, that is the imaginary part. So, it can be written as x1 x2 minus y1 y2 comma x1 y1 plus x2 y1. So, the multiplication of two complex number results a complex number. Next, division. Z1 divided by Z2, x1 plus IY1 divided by x2 plus IY2. Now, I just multiply x2 plus IY2, here x2 minus IY2, both numerator and denominator, x1 plus IY1 into x2 minus IY2. So, x2 minus IY2 is multiplied in both numerator and denominator term. In that of numerator we have multiplication as x1 x2 minus I x1 y2 plus I y1 x2 minus I square y1 y2 divided by its multiplication as x2 square minus I square y2 square. Here we have x1 x2 plus y1 y2 plus I x2 y1 minus x1 y2 divided by x2 square y square minus 1 minus minus plus y2 square. Here I square is equal to minus 1. x1 x2 plus y1 y2 divided by x2 square plus y2 square plus I x2 y1 minus x1 y2 divided by x2 square plus I2 square, that is a complex number. This is the real part, that is the imaginary part. So, the division of two complex number results a complex number. In case of algebra of complex number, we see addition, subtraction, multiplication and division in case of complex numbers. Now, we have to study some properties of algebraic operations in complex numbers. Properties of algebraic operations on complex numbers. Let we consider three complex numbers as Z1, is equal to x1 plus iy1, Z2 as x2 plus iy2, Z3 as x3 plus iy3. So, we have addition is commutative, addition is commutative means Z1 plus Z2 is same as Z2 plus Z1. We can prove that one. We know Z1 is equal to x1 plus I1 iy1. So, Z1 plus Z2 first we write, therefore, Z1 plus Z2 is equal to, in place of Z1, x1 plus iy1 plus Z2 x2 plus iy2. Addition of two complex number, first addition of real parts x1 plus x2 plus I y1 plus y2. So, x1 plus x2 plus y1 plus I whole into y1 plus y2. And Z2 plus Z1. Written as x2 plus I y2 plus x1 plus I 1. So, x2 plus x1 plus I y2 plus y1. So, that term is equal to this term. So, Z1 plus Z2 is equal to Z2 plus Z1. So, addition is commutative in case of complex number. Similarly, we prove another algebraic operations, the properties of algebraic operation, as addition is associative. Addition is associative if Z1 plus Z2 plus Z3 is equal to Z1 plus Z2 plus Z3, that can be also proved in that manner. So, addition is associative. Next, here we have to note that in case of addition, as we show, if 0 is added to a complex number, we have the same result x plus iy plus 0, which is same as z. Therefore, 0 is said to be as the additive identity of Z. Additive identity of Z. 0 is the additive identity of Z. Similarly, when we add the negative of that complex number, so x plus iy minus x minus iy, we have 0 result. Therefore, minus of Z is called additive inverse. Additive inverse, adding these two numbers results 0. So, that number is said to be the additive inverse of another number. Minus Z is called the additive inverse. These two are referred for that of addition case. So, addition is commutative and addition is associative. In case of multiplication, we have another properties as multiplication is commutative. Multiplication is commutative, that is Z1 plus Z2, Z1 into Z2 is equal to Z2 into Z1. Anybody can prove it by taking the values of Z1, Z2. So, multiplication is commutative in case of complex numbers, and multiplication is associative also. Multiplication is associative, that means Z1 when multiplied with Z2 and Z3, it is same as Z1 Z2 into Z3. Multiplication is associative, and multiplication is distributive. Multiplication is distributive. Z1 plus Z2 when distributed to that of Z3, we have Z1 Z3 plus Z2 Z3. So, multiplication is distributive in case of complex numbers, and in case of complex number also there exists multiplicative inverse. There exists multiplicative inverse. As we know, Z when multiplied to its inverse, we have 1, then that said to be the multiplicative inverse of that complex number. So, here multiplicative inverse is exist. Another way, if two complex numbers in which condition is said to be equal. So, equality of complex numbers. Let me take two complex numbers as Z1 is equal to x1 plus I y1 and Z2 as x2 plus I y2. If we say x1 is equal to x2, means the real part of Z1, that is the real part of Z1 is same as the real part of Z2, and y1 also equal to y2, y1 is equal to y2. y1, that is the imaginary part of the complex number z1, y2 is the imaginary part of the complex number z2, then z1 is equal to z2. Therefore, these two complex numbers are equal with each other. These two complex numbers are equal with each other. When the real part and the imaginary parts both are equal, then that complex numbers are said to be equal. Next, how graphically we show these complex numbers in the coordinate plane. Let us study the graphical representation of complex numbers. Graphical representation of complex numbers. So, here we draw x o x dash, y o y dash. That x axis stands for the real axis and y axis stands for the imaginary axis, and that plane on which these axes are drawn are said to be the complex plane. Complex plane, or we can say it as the argand plane. Argand plane, and that figure is said to be the argand diagram according to the name of the scientist Argand. That is the complex plane or argand plane on which these two axes, one is real axis and another one is imaginary axis, are perpendicular with each other. And here we take a complex number as z is equal to x plus iy. So, that complex number can be represented as, if I take a point here P, that portion is the x in x axis and this portion be y, and that of y axis in imaginary axis. So, the coordinate of that point P x y, and in complex we represent it as the resultant here, that point in complex represented as z is equal to x plus iy. Here O is the origin of that complex plane. Taking an example to show the complex number in a coordinate plane. Example, let us show the complex number 4 plus 3i, 4 plus 3i and minus 3 plus 4i in that of complex plane. Let me draw the complex plane. X o x dash, y o y dash, it is 1 2 3 4 5 minus 1 minus 2 minus 3, here 1 2 3 4 minus 1 minus 2 minus 3 minus 4. First term, that is 4 plus 3i. In x we have the point 4 and y we have the point 3. So, 4 y the point 3. Here the point let be 4 3 and that point associated with the complex number 4 plus 3i. Again minus 3 4i. In x axis real part is minus 3 and imaginary part is 4. So, minus 3 4, that point let q represented by minus 3 4, complex number associated with that point minus 3 plus 4i. In this way, these two complex numbers are represented by that complex plane, or we can say that is the Argand diagram. Next, modulus of a complex number. Modulus of a complex number. Taking let z is equal to x plus iy is a complex number. We can represent it in the complex plane. X o x dash, y o y dash. Here is the point P having the coordinate x y. That portion will be x, that portion will be y. So, OP square in figure, OP square is equal to PQ square plus QP square according to Pythagoras theorem. So, PQ square is equal to x square, QP square is equal to y square, or OP square is the magnitude of z is equal to x square plus y square under root, or magnitude of z is equal to what is x square? X is the real part of that complex number. So, real part of z square, what is y? That is the imaginary part. So, imaginary part of that complex number square and its under root. In this way, we calculate the modulus of a complex number. Taking an example, find the modulus of the complex number, modulus of 3 plus 4i, that is 3 square plus 4 square under root, that is 9 plus 16 under root, 25 under root, which is equal to 5. And again another example as modulus of a number as minus 3 plus 2i, square of the real part, that is minus 3 square, imaginary part 2 square under root, 9 plus 4 under root, it is under root of 13. The modulus of that complex number, this is the modulus of that complex number. Next, complex conjugate, another term, complex conjugate. What is complex conjugate? If z is equal to x plus iy, then its complex conjugate is z bar and it is defined as x minus iy. Okay. Graphically we can show it. Here is the real axis, that y stands for imaginary axis. So, if a point P having x y represent a complex number z, that is x plus iy, so its complex conjugate, the point Q, here x minus y, z bar, which is the reflection in the real axis of that point x y. Some properties of complex conjugate. Properties of complex conjugate: as the conjugate of conjugate is equal to z. Let me prove it. As we know, z is equal to x plus iy, therefore z bar, its conjugate, is equal to x minus iy. Then the conjugate of z bar is equal to x plus iy, which is equal to z. So, conjugate and its conjugate is equal to that number. Similarly, another properties of complex conjugate can be proved, as the modulus of complex conjugate is equal to modulus of that complex number z. 3. Z minus its complex conjugate divided by 2i is equal to imaginary part of that complex number z. Property number 4, z plus z bar divided by 2 is equal to real part of that complex number. Next, the conjugate of z1 plus z2 is equal to conjugate of individual term. Property number 6, z1 minus z2 conjugate is equal to z1 bar minus z2 bar. Property number 7, multiplication z1 z2 conjugate is equal to z1 conjugate into z2 conjugate. These properties can be proved like this. Again, z1 divided by z2 conjugate is equal to conjugate of z1 divided by conjugate of z2. The complex conjugate and its properties. So, with the help of this video lecture, we understand introduction to complex number, its notation, algebra in complex numbers as addition, subtraction, multiplication and division, next properties of algebraic operations on complex numbers as addition is commutative, addition is associative, additive identity and additive inverse, multiplication is commutative, multiplication is associative, multiplication is distributive, and exists a multiplicative inverse, equality of complex numbers. Next, graphical representation of complex numbers. Example, how we represented complex number in that of particular graph. Next, modulus of a complex number. Example, complex conjugate and its representation in graph. Properties of complex conjugates. So, with this useful and informative notes, let me wind up this session. Thank you.